Okay, good afternoon. We're going to continue on with this portfolio diagram lemma. But first, let me give you some homework. We'll say this homework is due 2 Fridays from now. So it's not this Friday, but the Friday after this. Okay. So we're going to have 3 exercises for from our textbook, Leuenberger. And in fact, this exercise 4, we're going to do essentially in class. Okay. Now, plus we have calculate the portfolio rate of return, expected rate of return, and the portfolio standard deviation for our portfolio of 2 stocks, assets 1 and 2. So we're going to use the numerical data that we have in our previous example when the correlation coefficient equals 1/2 and W1 equals 0, 0.2, 0.4, 0.6, 0.8, and 1.0. Okay. So we just calculate tables like we're going to have today for that. But for the correlation coefficient equals 1/2. Use our examples numerical data. Okay, and then we'll have, let's do an extra credit. Let me put that extra credit on the next page. And this extra credit is relatively easy. It just involves some algebraic gymnastics. We'll say check that W1 star, this is a W1 star that yields a minimum risk portfolio. Okay. Using the second order conditions. We'll see that we'll get this W1 star by taking the first derivative and setting it equal to 0. And, but then we have to check that we have a minimum here. And the second order conditions is what? That as a d squared sigma squared over dw 1 squared must be greater than or equal to 0. So the second derivative must be greater than or equal to 0. Why is that? Like, if you want a minimum and you have a function, say f of x, and this is x, and you have a function like this. This is a so-called convex function. Now, why do we want the second derivative to be positive? It seems to be, that seems intuitively wrong, because we're saying we want to make sure it minimizes the risk. But look at this. What happens is the first derivative is given by the tangent. We can see the first derivative starts off very negative, gets less negative. At this point, it goes to 0, and then it starts to get positive, and then more positive. So the second is the first derivative. And we should say, recall, first derivative is increasing. And this implies that the second derivative is greater than or equal to 0. The second derivative just measures the rate of change of the first derivative. We're going to, if we have, we probably will get to it, we'll calculate the W1 star. Okay, but let's continue on with our portfolio diagram here. Put this over here. Okay. Okay, so what we were considering the following in our example. Our example, we had what? We had that we have two assets, 1 and 2. So our portfolio consists of two assets, and we can say asset I has an expected rate of return of Ri, and it has a standard deviation of sigma I. Typically, these Ri's and sigma I's are given in percentages. It's always easier to deal with percentages when you're working numerical problems here, I find. So you have just two assets. Asset 1 has a higher rate of return than asset 2. But asset 1 also has a higher standard deviation than asset 2. So if you look at these, so both are efficient. Both assets are efficient. Okay, we get two efficient. And if we can show this graphically, we have the following. Let's do a graph here. This is good. This is R bar. This is sigma. Now, let's do 5, 10, 15. And let's go about 5 here. Okay. And let's go out to 10 here. Okay, so the first guy has a standard deviation of 6 and an expected rate of return of 14. So this is R1. Remember that Leuenberger is going to call that point 2, but it matters not. I prefer to call it point 1 because it's the highest one. And our second guy has a standard deviation of 3 and a expected rate of return of 8. So here it is, 2. Now, if we draw the domination cones of each of these guys, we see immediately we see that they're both efficient. Neither one nor two is in the other assets domination cone. So this implies both 1 and 2 are efficient. For this problem, for these data, you didn't need to draw it graphically. But graphically is always the easiest way, and you can't go wrong. We know that they're efficient because we know that 1 does not dominate 2. Even though it has a higher rate of expected rate of return, it has a higher standard deviation or risk. And obviously 2 does not dominate 1 because it has a lower expected rate of return, but it also has a lower risk. Okay, so this was the data we used. And the first time we misspoke, and we had, for 2, we had 6. Now, let's look at the case of the following. Let's look at the case. Let's call this case 1. And we'll say that row 1, 2 equals plus 1. Now here we claim that in our portfolio diagram lemma, we had something that looked like this. And here, this leg between 1 and 2, this leg corresponded to, of the triangle corresponded to row 1, 2 equals plus 1. Okay, so let's look at what happens when row 1, 2 equals plus 1 here. Okay, when row 1, 2 equals plus 1, we get the expected rate of return of our portfolio equals W1 R bar 1 plus W2 R bar 2, which equals W1 R bar 1 plus 1 minus W1 R bar 2. So this is linear, and this does not depend on row 1, 2. There's no row 1, 2 in this whole thing. So it's linear. It's linear. And the proportion that we put into asset 1. Now let's look at the portfolio standard deviation here. The portfolio standard deviation says that sigma p equals, this is of course going to be a square root, it's going to equal W1 squared sigma 1 squared plus W2 squared. Let's do this a little bit different. Let's say plus 2 W1 W2. Okay, row 1, 2 sigma 1 sigma 2 plus W2 squared sigma 2 squared. Okay, so what do we know? We know that this row 1, 2 this goes to 1. So what does this equal? And let's also substitute for W2, 1 minus W1. This is the square root, of course. Equals W1 squared, sigma 1 squared, plus 2 W1, 1 minus W1, sigma 1, sigma 2, sigma 1, sigma 2 here, plus W2 squared, sigma 2 squared. Take the square root of this whole guy here. Okay, good. So now let's look at this. We could call this guy here, this is akin to an X star. This is akin to Y star. And this term is just a 2xy term here. So what do we have? In terms of this, this then equals, or is analogous to the following: the square root of x plus y squared. X plus y squared just gives you this, x squared plus 2xy plus y squared. This is because rho 1, 2 equals 1. And for us, we get, so this just equals x plus y. Okay. For us, we get what? We get sigma p equals W1 sigma 1 plus, we get the x plus 1 minus W1 sigma 2. Okay. And this is also linear in W1. And the proportion of our portfolio that we invest in asset 1. Okay, let's put up a table with a summary of the calculations, and then we'll do a couple of them. Okay, so summary of calculation. What we want to do in the summary of calculations, we want to say that we want to do W1 equals, and then we want to say that the portfolio rate of return equals, and then we want to say that the portfolio standard deviation equals. So now we're going to go, for the W's, we're going to pick 0, 0.2, 0.4, 0.6, 0.8, and 1.0. Okay, yeah, we have plenty enough space. So what we're going to get is the following data, and then we'll interpret it. We're going to get, this is 8, 9.2, 10.4, so it's going up by 1.2 each 0.2 here. This is 11.6. This is 12.8. And finally, this is 14. Okay. Here we have the portfolio standard deviation is 3, 3.6. So it's going up by 0.6 every 0.2. Then it goes to 4.2. Then it goes to 4.8. So it goes up by 0.6, then it goes to 5.4, and then it goes to 6. Now, this guy is easy. If W1 is 0, means that we're at 2, right? Everything is, our whole portfolio, the portfolio just consists of asset 2. And if W1 equals 1, we're at 1. Okay, so obviously we know right away what the expected rate of return and the standard deviation are for those two guys. Now let's look at some other values. Let's look at 0.2 and 0.6. 0.6. Let's just look at these two here. And I'll let you check the other ones. Okay. So let's look at this 9.2. Where does this come from? Here we get RP equals what? Equals W1 R bar 1 plus W plus, let's just say 1 minus W1 R bar 2. Okay. So now if W1 equals 0.2, this equals 0.2. R bar 1 is 14 plus 0.8. R bar 2 is 8. So this equals 2.8 plus 6.4 equals, in fact, 9.2. So that checks out. Now let's look at the standard deviation here. Standard deviation, the portfolio standard deviation, sigma p equals what? Equals W1 sigma 1 plus 1 minus W1 sigma 2. Okay, so let's plug our numbers into that. So this equals what? We have 0.2 times sigma 1. Sigma 1 is 6 plus 0.8 times sigma 2, which is 3. And this equals what? Equals 1.2 plus 2.4 equals 3.6, which is exactly what we got there. Okay, now let's move over to W1 equals 0.6. I'm not going to do 0.4 or 0.8. Obviously, 0 and 1 are always trivial here. Okay, so let's look at this 11.6 and how this came about. So what does this equal? Now we have W1 equal 0.6. So now we get R bar P equals what? Equals 0.6 times 14 plus 0.4 times 8. Okay, so what do we get here? We get 6 times 14. We get 8.4 plus 3.2 equals exactly 11.6. So that checks out. Let's just check one other thing here. Let's check the standard deviation when W1 equals 0.6. Of course, this is for the case that rho 1, 2 equals plus 1. Okay, so now what do we get for the standard deviation? We get 0.6 times this, sigma 1, which is 6, plus 0.4 times sigma 2, which is 3. So this equals 3.6 plus 1.2 equals 4.8. So that checks. You could check the numbers on 0.4 and 0.8, but it's really not necessary here. Why don't we do this? Let's do something here. Let's see. Check these values for homework number 2. Add this problem to it. Just check those values for that, okay? I'm going to add one other thing to the homework, I think. No, we have it. Okay, now, we have one thing in the portfolio diagram that looked a little screwy. Remember, we had the portfolio diagram lemma. We have R bar P, sigma P. And what do we have here? Suppose we have, this is 1, and this is 2. Okay. Now, and this over here is so-called A. That is the expected rate of return of the zero risk portfolio. Now, we calculated this guy. This guy is for lambda, or rho 1, 2 equals plus 1. Now, when rho 1, 2 equals minus 1, perfectly negatively correlated, corresponds to these two legs. Rho 1, 2 equals minus 1. Okay, so why do we get two legs of the triangle for rho 1, 2 equal minus 1? Okay, and we only get one leg for rho 1, 2 equals plus 1. So let's look at this case a little more closely, and we'll see what we got here. Okay, good. So rho 1, 2 equals minus 1 is for perfect negatively correlated. Assets 1 and 2. So 1 and 2 are perfectly negatively correlated here. Okay. So what do we get? We get the portfolio standard deviation equals what? We're going to take a square root again, of course, but it equals the following. It equals W1 squared, sigma 1 squared, okay, minus 2w1, 1 minus w1, that's actually w2 here, sigma 1, sigma 2, this minus, the minus occurs because since rho 1, 2 equals minus 1. I actually skipped a step there. I should have put that in. Plus, now we have plus 1 minus w1 squared. And sigma 2 squared. And of course, we take the square root of this whole expression here. Okay? Let me move that up a little bit. Okay. Good. Now, here again, we're going to have an analogy here. We're going to call this term is similar to x squared. This term here is similar to minus 2xy. And we could have put sigma 2 as, no, that's okay. And then this term here is what? Is y squared. Okay, so now if we have that, what do we have? If we take the square root, let's do it here. So recall that if we have an expression that if we have something that equals x squared minus 2xy plus y squared, and we take the square root of that, what do we get here? Now we get that this equals either x minus y or minus x plus y. Okay, because all this is either x minus y squared would give you this, also minus x plus y would give you this here, because we're taking the square root of that here. We really skipped a step. We could say that that equaled x minus y squared or equaled the square root minus x plus y squared. And whichever is greater than or equal to 0. Okay, we want to make sure it's greater than or equal to 0 because we can't take a square root of a negative number and get a real number. Okay, so because we want this to be a real number. Be a complex number, sometimes called an imaginary. Like the square root of I. Okay. You can't have a negative, you can't take the square root of a negative number and get a real number. And we must have a real number here. So let's look at it in our terms. Terms. What does this equal? This equals the following. This equals sigma p equals what? It equals W1 times sigma 1 minus 1 minus W1 times sigma 2, or W minus W1 sigma 1 plus 1 minus W1 sigma 2, whichever is positive. Is at least non-negative. Whichever of these two guys is non-negative here. Okay, because the reason is that we can't take the square root of a negative number. Okay. Now, let's look at the calculations. Let's summarize the calculations. This is for row 1, 2 equals minus 1. Okay. So just like we did before, we're going to summarize the calculations here. And here we're going to see why we get these two legs. Right away you can see why we get these two legs, because we want to take whichever of those roots are real, that are greater than or equal to 0. So again, we'll say W1 equals R bar P equals sigma P equals. Okay, so this is for row 1, 2 equals minus 1. So here we're going to go, we're going to take a 0, 0.2, 0.4, 0.6, 0.8, and 1.0. Okay. So now RP is the same as we had before, because it doesn't depend on that. Let's look at what we had before. We can just fill that right in. Let's look at our previous table. Oh, good. Here we go. Our previous table said the following. It said that this was, of course, these two we know. Here, if W1 equals 0, it means we're at 2. So this has got to be 8 and 3 for asset 2. If W1 equals 1, we know we're at 1 exactly. So this one equals 14, 6. Okay, so let's look at some other values. Let's go across, first of all, the RPs. The RPs row stays the same no matter what the correlation coefficient. So this is 8, 9.2, 10.4, goes up 1.2. This is 11.6. This is 12.8. And then we go to 14 here. So it goes up by 1.2. So this is always, this is the same for any row 1, 2. So no matter what the value of row 1, 2 is, the expected rate of return always stays the same here. Now, let's look at the standard deviation. Now we're going to get something a little bit different. We start off with 3. At point 2, we get 1.2. At point 6, at point 4, we get 0.6, 0.6 here. At point 6, we get what? We get 2.4, 2.4. And at point 8, we get 4.2. Now, one thing we know about our data, what do we know about our data? That A equals 10, right? This is A. The point A equals 10, and at A, the risk is 0 here. So look what's happening here. So what leg are we on when we go from here? Now, we're on the following leg. We're going up this way. This is the leg we're on. This is our A. And here are the other legs. So we're going up on this leg here. And what you see is this is point 2 here. And you start off at point 2. Then you start heading up here. As you head up, look what's happening. You get lower and lower standard deviation or risk until finally your risk is 0 here. Then we turn around and we look at this guy. This is 1. And what do we get here? We get now we have something that goes like the following. So now we get this leg of the triangle here. So that's why there are 2 legs of the triangle that correspond to row 1, 2 being -1, or perfectly negatively correlated assets. Okay, let's take, let's do one more here. Let's turn this over. Boy, it's messed up. Let's turn this over. Let's try another case. It should be case 3, probably. And here we're going to say that row 1, 2 equals 0. So uncorrelated assets. So now we have two uncorrelated assets. They're not positively or negatively correlated. Okay. So let's look at the summary of computations. Also, before we do that, let's point out that now sigma p equals what? Equals the square root of w1 squared sigma 1 squared plus 1 minus w1 squared sigma 2 squared plus 2 w1 1 minus w1 rho 1 2, and rho 1 2 is 0, sigma 1 sigma 2, and we take the square root of this guy. Okay? Now, since this is 0, we know that this term goes out to 0. So it just drops out. So what we have is the square root of w1 sigma 1 squared plus 1 minus w1 squared sigma 2 squared. We'll take the square root of that. Okay. So that's akin to the square root of x squared plus y squared. Okay. And we can't reduce that, unfortunately. So let's look at the computations here. So let's do w1 r bar p sigma p. Make sure I wrote this down right. Yes, I did. Okay, good. Well, w1 equals 0, 0.2, 0.4, 0.6, 0.8, 1.0. Okay. Again, life is going to be easy for us if w1 equals 0 or w1 equals 1.0. At w1 equals 0, we're at 0.2, so we get 8 and 3. And at w1 equals 1, we're at 0.1. We'll just write that down. At 2, at 1. Okay. So this gives us 14 and 6 here. Now, the rest of the data go like the following. The portfolio expected rate of return stays the same all the time. So it's 9.2, 10.4, 11.6, 12.8, and then 14. So it goes up by 1.2 each time. Now, let's see what happens. Now, what happens is that this goes down to 2.68. And then we get 3.0, we get 3.79. I could have just said 3.8, 4.84. So you see what happens here. The portfolio standard deviation goes down and then up. And actually, this is a lower risk than either asset 1 or 2. So it's even lower than the risk of the lowest asset. So what we get is that for W1 equal 0.2, we get that sigma p equals 2.68, which is less than 3, and it's also it's strictly less than 6. 3 is equal to sigma 2, and 6 is equal to sigma 1. Okay. So when you look at this, let's look at this, what it looks like graphically. We're going to have something like the following. And you'll notice that this is clearly not linear here. We don't go up by, here we went up by 0.79, but if you add 0.79 to that, you don't get 4.84 here. It's not linear. Okay, so it's not linear in W1. So let's see what it looked like here. It looks like the following. Now we get something that looks like this. Let's draw this. Okay. 5, 10, 15. And here we're going to go 5, 10. So let's put our guys in here. So the first guy, number 1, is at 6, and it goes up to 14. So this is asset 1. Okay. Asset 2 is what? Is at 8, and the risk on that, the standard deviation, is 3. So about here is asset 2. And our triangle looks like this. We know A equals 10. We calculated that before. Okay. Now, let's look what happens. At 2, we know we're at 0.3, right? Here. So now we get, our risk gets lower than 0.3 here. So what's happening is this is actually going like this. This is for row 1, 2 equals 0. So for row 1, 2 equals 0, we can actually get a portfolio risk as measured by the standard deviation of 0. Okay. Let's just check that. Okay. Let's check that. Calculate. The W1 equals W1 star. That yields the minimum risk measured by the standard deviation portfolio when our correlation coefficient 1 and 2 are totally uncorrelated here. Okay. So how do we do that? How? This is very easy. What do? We take the first derivative of sigma p squared and take it, set this equal to 0, and solve for W1 star. Okay. So let's look at this. We probably won't be able to finish here. Sigma p squared equals W1 squared sigma 1 squared plus 1 minus W1 squared sigma 2 squared. This is for the case that the two assets are uncorrelated. Okay, so if we take the derivative, sigma p squared dW1 equals what? Equals 2W1 sigma 1 squared, right? Plus what? Plus let's expand this guy. This 1 minus W1, we'll have to expand this, is 1 minus 2W1 plus W1 squared, right? Okay, so what do we get here? Nothing for the 1. For the 2W1, we get plus 2 sigma 2 squared plus what? Plus, now we have a W1 squared plus 2 W1 sigma 2 squared. Okay, let's see what we got here. Oh no, this should be minus. Give me a break here. Here we have minus 2 sigma 2 squared. Minus 2 sigma 2 squared, very good. So this equals what? It equals 2W1 times sigma 1 squared plus sigma 2 squared minus 2 sigma 2 squared. And let's set this equal to 0. If we set this equal to 0, we get the following. We get W1 star, and we'll finish on this note. We get W1 star equals what? Equals sigma 2 squared over sigma 1 squared plus sigma 2 squared. And this is for rho 1, 2 equals 0 here. And so what does this equal? This equals 3 squared over 3 squared plus 6 squared. Okay, so it equals 9/45, or equals 0.2. So this is exactly what we got. This is the W1 that yields the minimum sigma p for rho 1, 2 equals 0. Okay, I think we're about out of time now. I think we're over out of time. Okay, thank you. Yeah, we are.